Welcome to this interactive session on lab digital transformation. In this module, we'll walk through a realistic case study of a pharmaceutical quality control lab, Case X, and show how it progresses from a semi-digital state to a validated, connected, and intelligent digital twin ecosystem. This journey is guided by both user-centric transformation and IT systems architecture. Let's begin. Chapter 1: Understanding Case X. The starting point. Case X is a mid-sized pharmaceutical company with a traditional QC lab. It operates with manual sample logging and paper-based SOP standalone instruments, HPLC, UV-Vis, pH meter, with no central data capture, and old LIMS system used only for sample ID generation, no integration with ERP, manufacturing, or stability systems, frequent audit observations due to data traceability issues. Objective: the goal for Case X is not just to digitize records, but to transform the lab into a predictive, validated, and fully integrated digital twin environment over 24 months. Chapter 2: The 5 Pillars of Lab Transformation. The journey follows 5 strategic pillars, applied step by step. 1. Process harmonization. Review all SOPs, remove redundancy, and standardize terminology. Map current workflows, as is, and design future-ready digital equivalents aligned with regulatory requirements for data integrity and 21 CFR Part 11. User role. Scientists and quality personnel co-develop electronic-friendly SOPs with business analysts. 2. Platform architecture and integration planning. Here we introduce the foundational IT view. System architecture layers. Injection layer captures raw data from instruments like HPLC, balances, pH meters. Tools. Chromatography data system, CDs, instrument middleware, OPCUA adapters. Method: real-time data injection via API or file watches. Database layer stores validated and structured data. Centralized LIMS and SDMS repositories designed with audit trails, timestamps, and Alcoa Plus compliance. Distribution layer makes data available to other systems, ERP, QMS, MES, dashboards. Enables batch release workflows, analytics, and reports. Its role: solution architects and system owners define APIs, secure channels, and audit log replication. User role: process owners validate how test data maps into batch records and reports. 3. Instrument and system connectivity. Case X moves from isolated instruments to a central SDMS and CDs hub. All critical devices are mapped for instrument output format, text, PDF, XML, data ownership and storage. Lifecycle integration triggers: manual, automated. Example: HPLC result files are auto-uploaded to SDMS, parsed for result values, then injected into LIMS. IT role: middleware setup and validation, e.g., LabX, Empower, OpenLab. User role: approves automated result transfer logic and conducts user acceptance tests. 4. Data governance and validation layer. This step embeds compliance by design, user access control based on role matrix, enforced review and approval workflows, audit trail monitoring and deviation alerting, auto-generation of validation test cases and traceability matrices. IT role: builds validation framework and system monitoring tools. User role: participates in test execution and ensures business logic is captured. 5. Analytics and digital twin modeling. With data harmonized and structured, Case X builds its digital twin layer. Each product batch has a virtual representation method. Performance is tracked and trend alerts trigger based on statistical prediction of potential OOS or instrument drift. Simulations forecast lab capacity, scheduling conflicts, and resource allocation. IT role: deploys analytics engine with lab KPIs and real-time dashboards. User role: uses visual models to manage lab priorities, review cycle times, and investigate outliers. Chapter 3: Implementation timeline. Phase 1: foundation setup, months 0 to 6. SOP harmonization, ORS development. New LIMS procurement and basic implementation. Instrument inventory, classification, and connectivity roadmap. Phase 2: system connectivity, months 7 to 12. SDMS and CDs integration. Injection layer configured with 10 plus instruments. Legacy data archival and new data mapping. Phase 3: automation and compliance layer, months 13 to 18. Workflow automation for stability, dissolution, and batch release. Validation protocol execution and audit readiness. Dry runs. Training and change management. Rollout. Phase 4: Digital Twin launch, months 19 to 24, real-time analytics dashboards, lab modeling for resource optimization. Predictive deviation alerts and method lifecycle management. Chapter 4, Outcomes and benefits after transformation. Case X now operates with 90% automation in sample logging and result entry, real-time review cycle monitoring, no audit findings for data integrity in 2 consecutive inspections, capacity to simulate workload, test throughput, and stability chambers using digital twin models, seamless collaboration between IT and QC teams, enabled by shared data models. Chapter 5, Lessons learned. Transformation is not tool deployment, it is capability development. IT architecture must serve the business workflow, not the other way around. Digital twins require foundational system maturity and traceable data. User involvement at every layer is non-negotiable.